Hi everyone, in this video we are going to solve the moments worksheet from Physics Unit 1. This question paper is actually compiled of all the questions from the year 2024 all the way to 2014, and in this question paper you will actually know if you solve this question paper it will be better for your understanding for momentum and also work energy power. All these concepts are added in this worksheet. Okay, so these are actually taken from question papers, so it was tough for me to separate the three topics separately. Now they are all in combined, so if you want to revise this, like these topics, I think watching this video or solving this paper will be much more helpful for the revision process. Now, this worksheet is actually divided into two sections. The first section is for your MCQs, and the second section is for your detailed theoretical questions. Okay, so let's start with the first question. Question 1, it says the uniform meter ruler of mass 100 gram is supported by a knife edge at 40 centimeter mark and a string at 100 centimeter mark. Okay, like this entire ruler is supported by like, two things. One is that this pivot, which is at the 40 centimeter mark, and the other is this 20 gram mass, which was connected to the meter ruler through a pulley over here. And it is also stated that the string passes over a smooth frictionless pulley and carries a mass of 20 gram as shown in the diagram, and at which mark on the ruler must 50 gram must be suspended so that the ruler balances over here. Now in order to balance everything over here, one thing we need to do is that we need to understand that there are a few terms. For example, uniform over here, uniform meter ruler. This indicates that the weight of the meter ruler itself is going to act from the center. So this one indicates that weight act from center. Weight acts from center. After this, it was also stated that the mass of your meter ruler was 100 gram. That means weight over here for the meter ruler will be 100 into 9.81, right? All the masses will be multiplied with 9.81 to find out the corresponding weight for that mass. Now over here, I'll draw a free body. I will just draw the forces over here which are acting on this meter ruler. Now it was stated that it was a uniform rod. That means the weight must act from 50 centimeter, as the total length was 100 centimeter. So this is approximately 50 centimeter, and this is the point from where your weight will act in the downward direction. Weight was 100 gram, and in moments mass is always measured in kg, right? So I'll just convert that into kg. So you have 0.1 g over here. The g over here stands for 9.81, by the way, not for the unit of gram. I've already converted the gram into kg, so that 100 gram becomes 0.1 kg over here. Another thing is 20 Newton, which was connected over a pulley to that meter ruler, will actually exert upward force. Because think of it like this: this is your object, right? And I'm going to connect this end with a pulley. And obviously, in this case, what the mass will be providing a downward force, and because of the downward force, the pulley will be pulled in the upward direction. So that 20 Newton force will create an upward force for this pulley. Other than that, again over here the weight of this force, or the force of this mass, is going to be 0.02 g. G again stands for 9.81, and I converted this kg, so I converted this mass in gram to kg, which is 0.02 kg at this. We need to now place a mass of 50 gram on this line. Now again, one thing over here, the pivot was at 0.40, so I'm going to measure all the lengths, like how much this 20 Newton, 20 gram, or the weight of the meter ruler was from this pivot. Okay, I'll always take the readings with respect to the point of pivot, which is at 40 centimeter. So this is 10 centimeter in that case, right? From 40 to 50, you're going to get 50 centimeters, and then from 40 to 100, this is 60 centimeter. It is going to be 0.6 or 0.1 meter, because again in moment distance is measured in meters, right? Okay, after this, I'm going to consider that I'm going to place that 50 Newton force, 50 gram force, which is going to be 0.05 Newton, 0.05 G Newton. This force will be placed on this section, which is approximately 8. Let me just say that this is x meters away from that pivot at the point 40. Now I can use the total momentum. So total moment clockwise is equals to total moment anti-clockwise situation over here. So total moment anti-clockwise is equals to total moment clockwise. In the anti-clockwise direction was that only 20 gram force over the pulley, and all the other forces, this weight of the plank and this extra 50 gram was acting in the downward direction, so they would make the plank move in the clockwise direction. So in that case, now you have 0.02 gram multiplied with 0.6. This will be equals to 0.1, sorry, not gram, 0.1 g gravitational acceleration, and after that you have this multiplied with 0.1 because it was 10 centimeters away from the pivot, so that will be 0.1 meter, and this will be added with that 0.05 g with x. Right now, if I have to just make x the subject of this equation, it will be x 0.02 g multiplied with 0.6 and then 0.1 g multiplied with 0.1, and this entire thing will actually be divided by your 0.05 g. Now again, after this, what happens? If you calculate this, you're going to get 4. So in this part, we're going to get 0.04 meter. If you convert this into centimeter again, it will be 4 centimeter. Problem is, this is 4 centimeters from the pivot, which was already 40 centimeter from this left side end, right, from the zero reading. So if you want to find out the reading on your meter ruler, that reading must be with respect to the zero reading, 0 centimeter, not with respect to the pivot, which was 40 centimeters from the 0 centimeter unit. So at this part, since you got that, okay, it was maybe 4 centimeters away from this pivot point, in that case, the total length is going to be 40 plus 4, right? So our answer would be 44 over here. So 44 centimeter. The mass of 50 gram object was supposed to be placed at 44 centimeter reading on this meter ruler. In that case, option C is your correct answer, right? So we are done with question 1. I hope question 1 was clear for all of you. We'll move on to question 2. Question 2 says that two equal masses travel towards each other and on a frictionless air track at speeds of 60 and 30, they stick together on impact. And what is the speed of the masses after impact? Okay. Now it says that this is the situation for before collision, and let me draw a diagram for after collision. For after collision, they are going to stick together and they will travel in the same direction with one combined velocity. Now, it was also stated that both the particles have same masses. So, that means if the particle of this, like this first particle has a mass of m, in that case, this second particle should also have the mass of m kg or m whatever the unit is. And another thing, over here, before collision, they are traveling in the opposite direction. That means one will be considered as positive and the other will be considered as negative, and after collision they are both traveling in one combined velocity. So over here what happens is that I'm going to consider one direction as positive and one as negative. So it's my opinion that I'm going to consider this as positive and this as negative, which means this after collision will also be positive. um, this is going to be what, 60 m, and this is going to be 30 m, right? Mass into velocity is momentum, and over here this is going to be m plus m multiplied with velocity, because this time the two masses will get added together to give you the final, like, can be multiplied with the final velocity. So from this part again I can use the similar equation. Sum of momentum before collision equals to sum of momentum after collision. Now for before collision you have this 60 m minus 30 m is equals to m plus m is going to be 2mv, right? So I'll just make v the subject. 60 minus 30 is 30 m divided by 2m. Masses gets cancelled out. 30 over 2 is 15 meters per second. In that case, option A is your correct answer for this situation, right? Now, this is the concept for, like over here, we're actually using the theory that sum of total, conservation of momentum, that total momentum before collision is equals to total momentum after collision, provided that no external force acts onto the system, right? That was your law of conservation of momentum. So, LOCOM was used over here. Okay, then we'll move on to the next question. Question 3 is also similar to question 2. It says that a ball of mass 2 kg traveling at 8 and strikes a ball of mass 4 kg traveling at 2. Both balls are moving along the same straight line as shown. After collision, both balls move at the same velocity. That means after collision, they will again stick together and move with a constant velocity. Now, in this time, this is your before collision, this is your after collision part. For that before collision, I'm going to write it like this: sum of momentum before collision, sum of momentum after collision. Now, for this sum of momentum before collision, you have 8 multiplied with 2 plus 4 multiplied with 2 is equals to 2 plus 4, 2 plus 4 multiplied with v. From this part, I'll just have to make that v subject of the equation. 8 into 2 is 16, so 16 plus 8 divided by 6, which is going to be 16 plus 8 divided by 6 is actually 4 centimeter. So 4 meters per second. In that case, final velocity after the collision, when the particles are combined together, they were both moving with this 4 velocity, 4 meters per second velocity. So that means answer A is your correct answer. So we'll move on to part question 4 again. Question 4 says that a weight of W hangs off from a trolley that runs along a rail, and the trolley moves horizontally through a distance P, simultaneously raising weight through a height of Q. As a result, the weight moves through a distance R from X to Y, and it starts and finishes at rest. Over here, this part is very important, that it starts and finishes at rest. That means over the time, there was no change in velocity, or there was no actual velocity gained by the particle, right? So over here, velocity was zero. This entire concept, velocity was zero, indicates that if velocity is zero, the object must not have any kinetic energy during the start or end of the journey. So Ke is also zero. That means we cannot use kinetic energy over here, as velocity was zero. How much work is done on the weight during this process? Work done may basically indicates any kind of energy, right? Over here, even though your weight was actually traveling this r distance, but it has risen a height of q, right? And the only force, I mean, the only type of energy that is available over here is due to this increase in height, which will be your gravitational potential energy. So in this case, work done is going to be equals to gravitational potential energy, which was mgh, right? Mg itself is weight and h over here is q. So you can write that wq is your final answer, which is option C over here, wq. Yeah, then question 4 is clear. We'll move on to question 5. For question 5, it says that two balls x and y approach each other along the same straight line and collide elastically. Elastic collision means that no energy was lost during the collision, and these type of collision are actually used to, in the situations for law of conservation of momentum, right? So elastically means, no energy loss, and low form law of conservation of momentum can be used for this type of scenario. We can see that the speeds are ux and uy respectively, and after the collision they move apart with speed vx and vy, and the directions as shown in the diagram. Which of the following equation is correct over here? Now their masses are not provided over here. Maybe their masses are quite similar in this case, that's why their masses are not provided. Two balls x and y approach each other along the same. The speeds are this and this. After collision, they move apart with speeds this and this respectively. The directions are shown on the diagram. Which of the following equations is correct, right? I mean, over here, I'm going to take direction towards right as positive. For this kind of cases, when you have double directions involved in cases for momentum, you should always assign one direction with either plus or minus. So in that case, I'm going to take the direction towards right as positive, which makes your sum of momentum before collision. So this is sum of momentum before collision is equals to sum of momentum after collision. That means low com can be used over here, right? Law of conservation of momentum, low com can be used over here. So we're using that. As I'm considering right as positive, in that case this will be positive and this will be positive, but this will be negative and this will be negative, right? So at the initial stage, you are going to have m ux minus m uy is equals to m uh, dx plus m plus, sorry, 1 minute. It's going to be minus m dy. So we can clearly understand that masses over here were equal for the two balls. So masses gets cancelled out. As you can see on the four options, masses were not involved. So that means the two balls must have the equal masses. And then you have ux minus uy is equals to vx minus vy. Wait 1 minute. Vy was positive, right? Because it was in the right direction. So in that case, will be minus vx plus vy. Right. Now after this, what they did over here is they are assuming that one direction is positive over here. This is positive and this is negative. This is negative and this is positive. Okay, so in this situation, you just have to, the directions are shown in the diagram, which of the following statement, the equations is correct. Over here, momentum is only negative or positive because of velocities, right? Now in this question, they were talking about speeds only. Speed is a scalar quantity, so the directions doesn't actually are involved in the calculations for speed. So if you're working with speed, then these two, like these signs over here, doesn't actually have any importance because they are speeds. Speeds doesn't have any specific direction. So what they're using over here is that everything will be positive at the end of the day. This will be positive, this will be positive. So whatever you get, everything will be positive. In that case, ux plus uy is equals to vx plus vy. So everything is positive in this case. So in that way, option A is your correct answer. Quite tricky because you need to specifically focus on the term speed over here. Because if they were working about momentum specifically with velocity, they would have referred to that velocity with v or in terms of velocity in words, right? But they are talking about speed. Speeds are scalar quantities, so the negative signs should not be assigned over here. Okay. Now this was your working for question 5. We'll move on to question 6. For question 6, again it says a spanner is used to tighten up a knot as shown, and there is a 200 Newton force that is 0.25 meter away from the very center of your nut. And again, over here the distance from the nut to the outermost distance from the nut, outermost surface of the nut is 0.04 meter. Now it is saying that a force of F is applied at right angles to the spanner at a distance of 0.25 Newton, 0.25 meter from the center of the nut, and when the nut is fully tightened, the applied force is 200. Like in order to fully fix the nut in that position, I need to apply 200 Newton force on the handle side of the spanner. And it says that what is a resistive torque in an anti-clockwise direction preventing the further tightening. Now, if I have completely tightened that nut onto the something, that means there must be some other force, right, which preventing further tightening. There must be some other force in this direction which is preventing tightening. Now that force will obviously be equals to what? The original value over here. Like you can find out the momentum over here. And what is a resistive torque? Torque means that you need to find out the anti-clockwise moment. Right? Torque means that if anything is rotating about a fixed point, that is known as torque, and that is also the concept for your moment. So you just have to find out the resistive torque or moment, which is going to be 200 with 0.25 meter, right? Which is going to be eventually 50 Newton meter. Because whatever force we're going to apply in the downward direction to prevent further tightening, there must be a 200 Newton force in the upward direction only. So in that case, now you're going to get your answer as C as your correct answer. That means for this 200 Newton force acting on the nut at 0.25 meter away from its center is going to provide a torque of equal force but in opposite direction, right? That is the only case over here. Okay, after this, question 6 is solved. We'll move on to question 7. In now question 7, it says that a hinged door is held enclosed in the horizontal position by a cable and there are three forces that act on the door: the weight and the tension and the H hinge force over here. Let me draw a free body force diagram over here in order to identify that how to distribute the forces actually. So this is your center of weight. This is your horizontal plane and this is your vertical plane. Now weight was entirely acting from the vertical plane, right? So weight will be entirely in the vertical plane. Tension over here was in this direction, and your hinge was actually providing a H Newton force in this direction. Now let's just assume that this is like theta and this is like alpha over here. Right? As my angles were not mentioned, so I can mention the angle at any way. I just want to explain this over here. So which means that weight was in the downward direction. This H Newton will actually create components. This is going to be um, T cos theta, and on the downward plane you have H sine theta, and for tension also it will create components T sine alpha, and over here it is going to be T cos alpha. Yeah. Now, in this case, they are asking you that which list gives a three forces in increasing order of magnitude. Like that means that from smallest to largest, right? So over here, think of it like this: because of this tension, right? The entire door is not toppling over, it's not like tilting over from the point hinge. Why is that? Because there must be tension over here in the upward plane that must be greater than the overall downward forces. That means T sine alpha must be greater than weight and H sine alpha. Another thing over here that yeah, I mean over here tension is the maximum value over here, right? Tension is the maximum, and then after that weight and hinge force is actually playing into role. Now again, one thing is that T cos alpha, H cos alpha, right? Over here, which one should be greater? As I already know that one component of tension was greater than both weight and this hinge force. That means over here, this tension should also be greater than the hinge force. That means the weight is actually the smallest one over here. The hinge force is the moderate one, and the tension is the maximum one in this case. So we are going to consider option C as your correct answer. That weight being the smallest, then hinge force, and then tension. Similar to this, we'll move on to question 8. It says that a mass is raised vertically in the time t, and increase in its gravitational potential energy was EP, and increase in its kinetic energy was EK. Over here, as the mass is being raised from the ground to a certain height, both kinetic energy and gravitational potential energy is increasing this time, right? Not kinetic energy is being converted to GPE. This time both are increasing for this particle, which means that what is the average power input of the mass? Average power input means what? Power indicates energy over time, right? So energy is total energy, because in this entire journey, when you are lifting that object from the ground to a certain height above the ground, it receives both kinetic energy and gravitational potential energy. So in that case, total energy will be EP plus EK divided by time. Total energy divided by time will give you the total power input in this case. So in that way, option D is your correct answer. We'll move on to questions 9. So question 9, it says that a uniform beam of 50 Newton, 3 meter long, again over here, uniform, right? Uniform indicates that weight must act from the center again, right? Over here, weight must act from 1.5 meter, as the total length of the beam was 3 meters over here. Okay, and it was supported to a pivot situation at 1 meter from the left hand side, and a load of W Newton is hung from the end, and it makes the entire beam in equilibrium. That means like moment can be used, like total moment before collision, total moment after collision can be used over here, and the diagram is shown. We need to find out the value for moment over here. Okay. In that case, obviously there's this force acting in the downward direction, and there was also this weight acting from the center, which is going to be what, 0.5 meter from this pivot, right? I'm going to take the moment from this pivot, so all the distance that I'm going to add over here should be with respect to the pivot. So obviously the weight over here was 1.5 meters from each end, but from pivot it is going to be total was 1.5 minus 1. You're going to get half over here. So in that case, sum of Anti-clockwise moment is equals to clockwise moment. I can just write it like this: that weight will be multiplied with your 1 Newton, as it was 1 Newton out, say 1 meter away from the pivot, and this will be equals to 50 multiplied with 0.5, as weight was 0.5 meters away from the center. So we can write and get 25 Newton over here. That means option A was the correct answer. The weight of that W was 25 Newton. Okay, moving on to question 10. Question 10 is also easy. It says a barrel of mass 50 kg is loaded on the back of a lorry that is 1.6 meter high, and by pushing it up a smooth plank of 3.4 meter long. Like this is your barrel over here. This is your barrel over here, and you want to push this barrel up this plank, which is 3.4 meter distance, and the height increase over here is going to be 1.6, right? After that, the barrel will be loaded into the lorry over here. This is your lorry, by the way, and they want to find out the minimum work done in this case. In this situation, what happens? Components will be created over here. Like I'll place this particle over here. This is the vertical plane, this is the horizontal plane, and the weight will act in this direction. Weight was what? 50 G, 9.81 being the value for G, and I have to find this angle over here also. Whatever that angle is, that will always be equal to the angle weight with this weight makes with the vertical component. Okay, whatever this angle is, this angle would also be same. I can actually calculate the value of theta, because if you focus on that part, this was 1.6 and the length of that plank was 3.4. So I can use tan. So I can use sine cos tan and sine from that to use the value for theta. So that would be sine theta is equals to 1.6 over 3.4. So theta over here is going to be sine inverse 1.6 over 3.4. And you're going to get some value over here for the value for theta. Now again, one thing, this weight will be divided into two sections, right? The vertical component and the horizontal component. So the vertical component is going to be mg cos theta, and over here is going to be mg sin theta, right? And obviously there must be a F force, because it was pushed along this plank, right? So this F force, whatever the pushing force was, should be equal to this mg sin theta. So we can understand the force over here is mg sin theta, and it was traveled over this 3.4 meter length distance, right? So the minimum work done will be, work done is force into distance. Force over here is going to be F sin theta, which is going to be mg sin theta actually. Mg was 50 G, sin theta was 1.6 divided by 3.4, right? This was the exact value for sin theta. So I'm just going to use a fraction over here. And this will be further multiplied with the distance, because equation was force into distance. So in that case, you get 50, 1.6, 9.81 divided by 3.4 and 3.4. So you get 787.4. 84.8. 784.8. Now, if I want to keep this into two decimal places, this will be indeed 780 Newton, which is option set of Newton, 780 joules. So option C in that case will be your correct answer over here. Okay, then moving on to question 11. So for question 11, it says that an electric pump has an output power of 25 kilowatt and an efficiency of 52%. That means whatever the total input power was, out of that only 52% was actually used for that useful cases, right? And it is trying to find out that which of the following expression gives a rate in kilowatt at which energy is dissipated. Dissipated means that lost to the surrounding or wasted energy. You want to find out the wasted energy over here. So before that, let's find out the total energy input in that case, right? So total energy input will be, we're going to use that equation, efficiency is equals to useful power divided by total input power. After this, I'll just make input power the subject. That will be efficiency, sorry, that will be useful power over efficiency. For useful power, that will be already given 25 kilonewton. I'll just keep it in kilonewton because your answer also wants it to be in kilonewton. So 25 over, this is actually 0.52, right? It is in percentage. So if you convert it to data or magnitude, it's going to be 0.52. Now this gives you the value for the total input power, and out of this, how much was wasted? I mean, if out of the total 100%, 52% was actually in a useful case, that means 100 minus 52 gives you 48%. That means out of the total useful, so out of the total input power, 48% energy was wasted. So we can find out that wasted energy or energy dissipated is actually going to be 48% of the total input power. So it is going to be 0.48 multiplied with 25 divided by 0.52, which can be further written as 0.48 25 divided by 0.52, and that is your option C over here, right? So option C is your correct answer for question 11. We'll now move on to the next question, question 12. Now in question 12, it says that a uniform beam, again uniform, that means weight must act on the center, right? So a uniform beam of 100 Newton is pivoted at point P as shown, and there are weights of 10 Newton, 20 Newton attached at its two ends. We can clearly see this 10 Newton and 20 Newton. As this was a uniform beam, that means the weight must act from this point, from point B. Right. Why from point B? You can clearly understand that each section over here is 0.1 meter, right? So this entire thing is this entire thing is 1 meter long, and up to this is 1, 2, 3, 4, 5. This is 0.5, so that is exactly at the center. Okay. Now after this, we will move on. Weight was 100 Newton, and we need to find out that at what distance another 20 Newton can be attached. So I will actually, I'll call it at point X, and I'm attaching another 20 Newton at point X. Now I have to find out point X value, and obviously all the distances should be taken with respect to the pivot. The pivot was over here. That means over here from the pivot to point D it was 4 meter. From pivot to point this one other end was 0.6 meter, and then from pivot to point B is going to be 0.1 meter, right? As it only has one block and one block length was 0.1 meter. Okay. Now we are going to do the same calculation. Total momentum, sorry, moment in anti-clockwise is equals to moment clockwise. So I'll just write it down as 20 multiplied with x plus 20 multiplied with 0.4. This is equals to 10 multiplied with 0.6 plus 100 multiplied with 0.1. So from this part again, I'll just make x the subject. This 10 multiplied with 0.6 and that 100 with 0.1 actually gives you 16. Okay, the 16 minus the 20 minus, so 20 multiplied with 0.4 gives you 8. This one over here gives you 8. So we take that 8 from left hand side to right hand side, it will obviously subtracted and divided by 20. So 8 over 20, this again gives you 0.4 meter. That means the point P actually can be added 0.4 meters on this direction, like from towards left, or on this direction or also on this direction to make it in equilibrium. Right? So we just want to find out that at which point should a further weight of this plate. I mean, we're not going to attach it over here because we can clearly understand if I'm going to attach it over here, the entire pivot will actually topple over in that direction. Right? Will actually start moving in an anti-clockwise direction. It would not be balanced if I'm going to attach that extra 20 newtons in this direction towards the left of the pivot point P. So that case, in that means that there should be another 20 newton attached to the point D again, right? So that will be the only answer, that it should be attached to point D. So D is your correct answer over here. Okay, that's it then. We'll move on to question 13. Question 13 was exactly like a question 12, right? Over here, we have already drawn the components. Weight is given to you, and it was saying that you need to find out the work done as we're going to move the barrel a distance of 5 meter up the slope. So obviously, as I always do, draw the planes. If this is 30 degree, 1 into 10 to the power 3 means what? 1000, right? So I can write this is 1000 cos 30 degree and the backward force is 1000 sine 30 degree, and obviously in the upward direction we have reaction force. Now this force should be equals to this 1000 sine 30 degree. So at the end you have work done is equals to force into distance, where force is 1000 sine 30 degree multiplied with your what, 5 meter distance, which is going to be 1000 sine 30 degree and then multiplied with 5. So you have 2500 joules of energy, which can be written in standard form as 2.5 into 10 to the power of 3 joules. In that case, option B is your correct answer, right? Over here for question 13, option B is your correct answer. I hope question 13 was clear for all of you. We'll move on to the next question. Question 14. Now it says that in question 14, a ductile material is stretched into a tensile by a tensile force to a point beyond its elastic limit, and the tensile force is then reduced to zero. The graph of force against extension is shown below, and which area represents the net work done of the sample. Okay, net work done of the sample means that area for loading minus area for unloading. Okay, so for loading minus unloading. Now we can clearly understand, obviously the area under this graph will give you the work done, right? Because force into distance, force into extension will actually give you the value for your work done. So in that case, for loading, you have x plus y plus z, and for unloading, you have just z. So you can clearly understand z will be cancelled out from the equation, and the end you are just going to have a summation for x and y. So this is your answer. Option B, x and y. Summation of x and y will be the final answer for this case. Then we move on to question 15. Over here it says that this F Newton is applied on a beam at a distance of d from the pivot and theta degree. Now I will obviously draw components over here. This is the vertical component and this is the horizontal component. This is F sine theta and this is F cos theta. Now we need to understand that which combination will cause the largest turning effect. Largest turning effect means that in which combination it will have the maximum moment over here, right? So for the maximum moment, I think you clearly remember that equation for moment was force into distance, right? Which means that moment was separately directly proportional to force, and moment was again directly proportional to distance. So increasing the distance, increasing the magnitude of the force will obviously increase the moment. But there's another case also with respect to distance and force. We also need to focus on the theta over here, because in this case moment can only occur because of this vertical component, right? The horizontal component will not create any moment, as the pivot over here can only make the what is this beam over here move up and down, right? Move it up and down in clockwise and anti-clockwise direction. So the horizontal force over here will not play any role in the moment calculation. This one is only related. Now I already know that if I'm going to increase a value for theta, the value for the cos theta will decrease, right? I think we saw this in vectors classes or in other classes already, that if theta increases, right, the sine component of the theta would also decrease. But if theta increases, the cos component of theta would decrease, right? So in that case, over here, as I want to increase the value for moment, right? In that case, as I want to increase the value for the vertical component, if must increase, but theta over here has to decrease, because if theta decreases, then cos would increase, right? Because they are inversely related, theta and cos theta. So which means that force must increase, distance must increase, and theta over here must decrease. So in that case, large, small, right? Increase, decrease. So option B is your correct answer over here. This was your question 15. Let's move on to question 16. Okay, it says that a rigid uniform bar of length 2.4 meter is pivoted horizontally at its midpoint. Weights are hung from 2 points of the bar as shown in the diagram. To maintain a horizontal equilibrium, a couple is added to the bar. What is the torque and direction of this couple? Okay, now this was entirely 2.4. Weights are hung from 2 points of the bar as shown in the diagram to maintain the horizontal equilibrium. A couple is added to the bar. What is the torque and direction of this? Where was this added? To maintain horizontal equilibrium. Oh, sorry, to maintain horizontal equilibrium. Okay. Then let's just find out. For example, this one will actually make the entire bar move in a anti-clockwise way, and this will make it move in a clockwise way, right? So this is AC, and this is just C. Now I can understand all the distance has to be measured with respect to your pivot. In that case, this distance it was totally what 2.4 meter, right? Yeah, 2.4 meter. That means from 2.4, this is 0.8. 2.4 minus 0.8 these will be actually 0.4 and 0.4, right? 0.4 plus 0.8. Right, this entire length over here was 1.2 and this entire length was again 1.2. So 1.2 minus 0.8, this value will be 0.4 in that case. So now I'll try to find out the moment in anti-clockwise direction, which is going to be 200 multiplied with 0.8. So you get 160 Newton. And on the other side, if you multiply 300 into 0.4, this is going to be 120 Newton. Now I can Newton meter. Now I can clearly understand that there is 14 Newton meter more moment on the what on the anti-clockwise direction, right? So to make it balanced, I need to wait. I need to add something on the clockwise direction. So there should be something added in the clockwise direction, and how much is that? 40 Newton, right? Because the difference is 40 Newton. I can clearly see. So it should be 40 Newton meter clockwise. I should add something on this clockwise direction. So answer over here is going to be 40 Newton clockwise direction over here. Okay, question 7. I think this is exactly like the first, the third question over here we did, like this question. Yeah, this question is exactly like question 17. Right. Over here it says that a stone of weight 4 Newton on the Earth's gravitational field is moved from point P to Q, so P to Q and then to R along the same path, and how much potential energy does the stone gain? Doesn't matter if this pathway you use or this pathway you use. The increase in height over here was 30 meters, right? So in that case, it's going to be mg8. Mg is 4 multiplied with 30 gives you 120 joules. So option A is your correct answer for question 17.